Okay, this slide is just helping slide to recall the implication operation from Boolean algebra that I'll be using later, that something implies something, like P implies Q. So, and this is a truth table of it on the right-hand side, so hope you see that. And that says this implication is always true, except of one case, when premise is true and conclusion is false. So you cannot really conclude falsely from true statement. That's why it's false. Otherwise, it might be also a bit interesting to see that you can, from false, you can imply anything. All right, it's true. This implication. Okay, assignment axiom is a rather formal definition. You don't really need to dig deep in it. But simply speaking, that on the right-hand side, we have an expression E, which should be evaluated. And the result of evaluation is just an expression you can substitute to the left-hand side. This is premise that describes a state before. And this premise is also should include x, something say about x. And if you put E into x, then it should be true. Or in other way around, you can substitute x in post condition. So here comes an example that if x, especially this one, if x is initially 0 and we assign 1, it becomes 1. Furthermore, y is axiom because when you assign x to 1, the final state is x equal 1, and the initial state doesn't matter. You can just say true. It means any state, okay? Or false. But at the end, x is equal 1. And that doesn't need to be proven if it's written like this. Okay? Of course, if you write here x assign 1, x equal 2, that's wrong. So now inference rules, they describe effect of program statements. We consider some hypothetical language, but this is general enough, similar to C, that allows us to write parallel programs, in fact. So composition rule, semicolon. So people forget about what does it mean. When you write a program, you put semicolon at the end of, right? That means sequential execution. S1, then S2. First statement, then next one, right? And semicolon in between. So if you want to describe state before execution, P, and after execution, R, and you would like to prove it, that it's really like this, the state transition will be made after execution of two statements sequentially, then you need to prove two hypotheses, right? Which are on top, above. So you should prove that you introduce like intermediate state, you describe it, saying that if you start in P and execute S1, so then we move to Q, and if you start in Q and execute S2, then we move to R. So these two premises can be proven separately, and if it's rather simple statements, so you eventually end up with axioms, right? This is composition rule that describes execution of this semicolon between two statements. Now, if statement, we need some conditionals, right? We need to check condition, it either executes something or not execute. So here I'm taking just without else. It's enough, you know? Else is just for convenience. If true, then this, else, something else. But let's just consider without else. So it means that if B is true, execute S, otherwise skip, do nothing. So that's initial state, this is final state. Imagine that you have described it. B is some logical expression that evaluates to true or false. Boolean expression, S is statement or statements, it could be several of them. To prove that this is true, you need to prove again, two hypotheses because there are two cases here. Right? First one B is true and second one B is not true. So if B is true, and the initial state is P, this is end, right, logical end. After execution of S, we end up in Q. This you need to prove. And another hypothesis or premise for this conclusion describes a scenario, a situation, a case, if you will, when B is false. Saying P and not B implies Q. Okay, that we move to Q. That's implication that I have shown on previous slide, this operation I'm using here. Any questions so far? Okay, maybe it's a bit confusing. We have not reached the point, start using it. I'm just introducing inference rules. I'm not using it yet. While statement. I think while loop is enough. We don't even need for, right? Because for can be implemented as while, but while is general loop, right? While B, iterate, and when not B, then we terminate. Okay, it has been proven in semantic of programming languages that this while loop can be approximated with one iteration if you introduce so-called loop invariant. It's a predicate which is true before loop starts and after. And the difference is that before loop starts, so if B is true, it iterates. When B becomes false, it ends. Okay? So therefore, final state is still loop invariant and not B. So because it stopped iterating. It breaks the loop. And to prove this, you need just to prove one iteration saying that I and B, it iterates and ends up with I. And if B is still true, it keeps iterating. There's some kind of approximation of this with this, and you prove just this would be enough to prove. To prove that loop executes. Okay, this is a helping rule. This helping rule helps if needed, so you don't need to apply it, but if needed, it's just for efficiency and effectiveness of proof and to simplify. It's a rule of consequence that allows to modify predicates, to simplify them or to say them more precisely. Okay, saying that P prime implies P, Q implies Q prime, so therefore this statement can be, this predicate and this predicate may be too strong, so you can simplify them. P and Q, maybe this proof is easier to do, for example. Simplify or make them stronger. What means implication? So where's it's to right? Do you see any? Okay. For example, P prime could be x equal 5, okay? And P could be x more than 0, okay? This one implies this one, okay? But not vice versa, of course. Right? So if x is strongly equal 5, then it's definitely more than 0, right? So that means that you can cover more states and make it weaker, your precondition. Weaker means it's not so strong, right? So it's not precise. It covers more states. And maybe the proof is easier. Right? And similar with Q. But this is helping, it's just for, that's why I said that it's semi-automated. You might change this. Now, because we are talking about parallel program, we need something for parallelism. What do we need for parallelism? We need for synchronization something that's a wait statement, such dialect, and plus core statement would be enough maybe to write parallel programs in our hypothetical language. So again, to remind you, we have assignment, we have the sequential execution, semicolon, composition rule, we have if statement, without else, but it's okay, it's general enough. We have while loop, also general enough, you can express for loop through while loop. And it's enough, right, to write in your program. We don't need go to. Now, a wait statement. It's similar to if statement. You remember if I go back, if statement says that when B is true, we execute S. When B is not true, we just move to the state Q, skip it without executing Q. So await is stronger because here we are waiting, right? So we need to wait when B becomes true. So therefore, to prove that this is true, we need to say that when B becomes true, P and B, after execution of S, we move to Q. There is no other case like in if statement. It's only one case. Cause statement. So cause statement that looks like this. So in general, this is cause starts, that's cause ends, and there are several threads, in this case n threads. And in general case, each thread might execute different statements, right, different things. So it's 1 up to Sn. Okay? And this vertical line is just separate threads from each other. So for each thread, we can consider each thread in isolation. Saying, okay, let's look at S1. What is the initial state for S1? Is this one, P1, okay? And similarly for other threads. But initial state, like predicate for the entire cause statement, should be conjunction of all initial states for threads, so that they start all of them, right? Conjunction is AND operation. Huh? You remember conjunction, disjunction? You're looking at me like you hear this first time in your life. AND, right? So it should be P1 and P2 and P3 and P4, conjunction. So all this should be true. That statement starts, executes, and finally it moves to final state, where you can describe for each thread in isolation, but the final state for all threads, all of them they complete, should be conjunction of final states for all threads. And to prove this, you can prove each thread in isolation. You have I theorems or premises for each thread, right? But the most essential, what is highlighted here in red, that these proofs should be interference-free. It means that one proof should not violate another. Okay? So all of them should be proven. But if it's happened that you prove something for thread I, and this proof violates, it means that it makes false for thread J, that means that this is not theorem, so it's not really true. Right? Because this, for example, some state they contradict each other. This interference freedom is important in this proof, and this process is they interfere with each other if they execute something, one of them that violates precondition or postcondition in another process, right? It becomes false. Some kind of contradiction occurs. And why it might happen? Because they're hidden shared variables. Okay. Let's say one thread is claiming saying that x never gets to 0, and another proof saying that x is less than 0. All right, so they might violate each other. So this non-interference, okay, we are not going to deepen it, but the situation is that, as I said, that if it's happened that there is precondition A for some statement A, and C is a critical assertion in another process, so it's like pressed or postcondition in some other thread, C, but then execution of A should not change C. And if it changes to false, let's say, then it means that these two threads, they interfere. So one thread suddenly change the state in another one, and that state is false, it's bad state, and that means violation of proof of another thread. Okay, that's interference. So therefore interference you can think of is like thread interaction, but in the wrong way. Okay, of course threads, they interact with shared variables, that's what they should do, but if they interact in the wrong way, leading to deadlock or leading to incorrect result, that means interference. That's what we call interference. How to avoid it? So the very first cause of interference typically is just silly mistakes using the same names for variables which are in fact different. Okay? And why one can do that, I just simply forget that I have used X in one thread and now I start using it in another, but for different reasons, and it's shared variable. Or one cares about memory footprint and try to minimize number of variables, or to start reusing them. Saying, okay, here I used it before, now I'm going to use it again, but doesn't take into account asynchrony, that it's happened that these two uses might happen at the same time. This is so-called false dependence, okay, between threads, and you should avoid it. And how you do that? It's very easy. You just rename variables, right? Instead of using X in one place and another, use X1 and X2, or X and Y, something. So you need to disjoin variables which are not really the same. So also it may happen that your proof says violation, but in fact there is no violation. Why? Because when you are proving or describing states, you don't take into account concurrency, and your assertions are too strong to be proven, and that's why they're not provable. And why they're too strong? It's not because they're just simply wrong, because you didn't take into account concurrency. I can give you an example on the next slide. And also what is helpful, actually it's not really a way to avoid interference, but it helps to discover it and then to avoid it, it's to use global invariants. It's quite good that for some program or maybe for some fragment you'd specify some property in form of predicate that always true, should hold. Okay? Like semantically, according to functionality, and they just should see in this proof that this global invariant is really invariant. It never changes. And if it changes, that means something wrong. And I try to find this back. And of course, synchronization that delays execution until thread can proceed. And the idea here, why synchronization allows to avoid interference. Just imagine that threads are interfering. That one thread executes and violates something in another thread, put it in a bad state, and that thread just, let's say, deadlocks forever. Okay? Doesn't go. So how, by means of synchronization, you can do it in a way that you can prune the first thread, like delayed, until the second executes, and then this first one. So it means that you are trying to move through state space through safe states, good states, okay, by means of synchronization. And what kind of implication for programming logic, how it is? It means that you introduce some extra constraints in preconditions through this synchronization, like thread should be waiting for something to proceed. Right? You introduce this in precondition. Usually you just put some await statements somewhere. That's what synchronization is. Okay, disjoint variables, as I said, that two processes do not depend on each other, and hence they do not interfere. If right set of one process, this is right set, is disjoint, this is intersection, these are set operations here, from read and write set of another process. Simply speaking, they work on different memory. Okay? Like on different elements of array, on different domains, they do not interfere. Because there is no reason for them to interfere. Disjoint variables. But that's not always the case, because threads should interact through shared variables. And as soon as they start interacting, then you need to synchronize. That's the story. Weakening assertions, this is more related to proof. So imagine that there are, this core statement, there are two atomic actions, increment x and x plus 2. Okay? And the atomic, you see the single brackets, it means that they should be executed in any order, but one at a time. Okay? So initial state is 0, that's what, imagine that you describe it, and final state is 3. Now assume, don't look at this, assume that you are considering each thread in isolation. Okay? you write that the initial state for thread first is x equals 0. Final state is x equals 1. And furthermore, that it's an axiom, right? So that you just don't even need to prove it. So then we look at second thread in isolation again, right? Just like only one, this thread, nothing else. X equals 0, final state x equals 2. Now try to prove that after execution is x equals 3. There's no way to prove. Because this one says x equals 1, this one says x equals 2. How it happens that x equals 3? Why? Because we didn't consider this concurrency. Okay? Because threads are executed even in sequential order, one at a time, but OC means some kind of barrier at the end. Both threads should complete before proceed. So therefore, initial state for first thread can be either 0 when it starts first, or it could be 2 when it executes next, right, after this one. So the same story here, initial state for second thread can be either 0 when it starts first executing, or it can be 1 if it executes after this one. Okay? Because this one increments, makes it 1, so that this one reads x equals 1. This means O in logic. Okay? Any questions here? So then it means that you should weaken assertion. It means that your assertion was too strong, that it's only initial state. You should add one more state. And then it's provable. Then we just apply inference rule for co-statements, that precondition for co-statement should be conjunction of this one. If you you take conjunction between these two, and if you remember more or less Boolean algebra, so you eventually end up with x equals 0. And the similar story here. You take conjunction of these two, and you'll see that x is equal to 3. Okay. Right, and it's actually written here. Global invariant is very helpful because, as I said, for development especially, you describe some predicate, say something about variables, how they are, their range, how relations between them, which you believe should be always true, should be kept. And your program should preserve it, right? And that's some kind of indication of correctness and safety of it. So I should be true when process begin execution, and I should preserve by any assignment action, so it should be like always true after any statement. Why is good? Because if you know that this should be always true, and if suddenly you see through your proof that it's not true, that means something wrong. Of course, how to dig and to find bug, that's another story. But nevertheless, it's indication that something is wrong. Typically, but not necessarily, that you can express predicate, some assertions in form of typically, usually you say, global invariant and something, okay, before each statement, because global invariant should be always true. And in something can describe some specific state. It might be local variables. It's not necessarily stated here it's local, unlocal, but it could be also some global here. But I typically include some global variables, invariant. You will see example later. And synchronization is way, just again to remind you, it's a way to delay, to prune a process until it can safely proceed. And you do that by introducing some additional constraints to avoid interference, postponing some process, waiting for something. You put await statements whenever needed. Okay? And that allows you to hide internal states, making atomic action like critical section. And usually you apply mutual exclusion or condition synchronization. Okay. For example, here, if A interferes with C, what you can do, you can put a wait here, as I told you, right? So you postpone this A until it's not C, right, when it executes, or there is some B statement, whatever, that describes such that after execution of A, C becomes equal true, and so that this one should proceed. Otherwise, it will get stuck because C is never reachable. Yeah. Okay, just basically, again, you need to, that's the only way to delay. You need to find places where you should delay and wait for something. Okay? That's synchronization. You cannot speed up in this case. How to prove safety property using this programming logic? It can be done in a different way. One way to annotate your program, after each statement you describe a state, and then using inference rules you prove that final state of program is true. But describing state, you need some predicates and describe it you should describe good states. But sometimes it's difficult, and you start with bad state, right? That's maybe easy to express. And then what you usually do, you express bad state. I don't know, say the program deadlocks when this occurs. Maybe it's easier for you, okay? And then, of course, you need, in this case, bad should be false in every history. Therefore, you should annotate it with negation of bad, right? In state, that it should be good, like being always in good state. So therefore, it's a matter of convenience. If you're able to describe good states, you describe good states. If not, then you just describe bad and take negation of it. So if it's not bad, then it's good, right? And usually proof is done either through space state exploration, so there are special tools, semi-automated, of course, because state space can be very big, or it can be done by means of proving that I will show you now. One more way of proving, number 3, exclusion of configurations. Here you might say that you describe something here, precondition of here, and precondition of here, and say that if they occur, both of them at the same time, then it's bad, and maybe you need to prove that this one, is it really the case or not? Now it sounds a bit abstract. Let's go for example, and then it might become more clear. So assume we have as I said, that quite general way of interacting of parallel threads is producer-consumer. One is producing something, another is consuming. Okay? So at the end, it boils down that some data in producer are moving towards consumer. Okay? So therefore, let's just simplify this interaction by simple copy. So we assume that producer will be producing array A, like n values, like a stream you can think of. And eventually this A should derive to consumer. Okay? Consumer will get them in B, which is local variable for consumer. But they will be communicating through shared buffer. This buffer is buff, that one. And just for simplicity, we assume it's single slot buffer. Okay? For one placeholder for one item. So it means that producer will be producing, we just neglect what this is producing. It could be quite complicated process, but eventually it writes some results into this array, and then moves from this array to the buffer one by one, okay? Some stages, some point of time. And consumer, it will read buffer, but read is like destructive read, like extracting data from there, empty the buffer, into its local array B, from 0 to n. Okay, here's n plus 1, it should be n minus 1. Of course, the shared buffer becomes shared variable, and we need to synchronize access to it. So it should be accessed with mutual exclusion, so that the producer and consumer do not collide. One is reading, another is writing next data. And also condition synchronization in a way that consumer should wait until buffer is filled, and producer is wait until buffer is emptied to put something. So this synchronization requirement, we count number of produced and number of consumed items. P and C, these are counters. Whenever something is produced, P is incremented. Whenever something is consumed, buffer is emptied. C is also incremented, so we're counting them. So C could be not more than P, that's what it says, this predicate. Why? Because we cannot consume more than has been produced so far. And P should be at most C plus 1, could be, not should be, could be. Why? Because we have single slot buffer. We have already considered this predicate, and this is global invariant. It should be always true with respect to values of C and P. Right? In any state, it should be always true. Okay, that's a parallel program, producer consumer. Okay, there is no really production here. It's just only this fragment of copying. Right? So assume that this element A is already array is filled by some data produced, and that's what we are doing. This producer, it's waiting when P is equal C. It means that buffer is empty. Everything that has been produced has been consumed. Right? P is equal C. So then it places element into the buffer, and P is incremented plus 1. And P starts from 0. Right? And it does it. You can put for loop, but you remember that we agreed we will be using only while loop in our hypothetical language. So it will be doing that until P reaches N. So consumer, it consumes. It knows how many items to consume and items. So it waits when buffer is full, P is more than C, because something has been produced. And then it reads buffer into this slot pointed to by C, and C is incremented plus 1. So this increment will trigger this await, and this increment will trigger that one. Trigger means might become true await. So this is a synchronization requirement, global invariant, but on the other hand, maybe it's not enough because it tells only about this counter C and P. It doesn't say nothing about other memory that we have. We have buffer, we have this array A, local for producer, and the array B, local for consumer. So therefore, you can make an effort and say a little bit more about this program. And that's what I say here. PC stands for producer consumer predicate. That includes synchronization predicate, this one that we already stated. And, it says and here. We say that array A is not altered. That's what I'm saying here. That A contains those values. These are values A. Okay? You can write them in an abstract way. And when P is equal C plus 1, what does it mean? It means that buffer is full. It includes something in it, right? So we produced more than consumed. Let's say P is equal 10 and C is equal 9. Okay? In this case, buffer contains this value, which is indexed or pointed to by P minus 1. Okay, you can check it. That's really, that's how it is. And this is implication. Of course, it's not necessary that you say this, but maybe it's good, especially this predicate is good because it also includes child variable buff, and in some way it captures, helps to come up with a weight. Unfortunately, there is no any formal procedure how to extract await statements, not extract, how to synthesize them given this or this, right? So it's like you as a programmer should do that. And that's how a proof might look like. Sorry for small font because it was copied to picture. So the producer consumer that you have seen before, but now it is annotated. Annotated that after each statement, like PP plus 1, you put some, and before and after, you put predicate that describes the state. accordingly how we introduce this global invariant, PC, and so forth. So you see, if you look at producer, before while loop, we have a PC should be true. PC stands for producer-consumer invariant, and P is less or equal to M, right? Before while loop. And that's what we are devoted is like IP, which is loop invariant in producer. For while loop, you look at inference rules and how it should be described. And after the loop, PC still holds, but it says and P is equal N. It means that loop breaks. So we iterate it 10 times. Okay? So inside the loop, it says PC. You see that PC comes always everywhere, right? Because it's global invariant. It says and P less than N. It means that we are iterating. We are inside the loop. Okay, P hasn't reached N yet. Okay? So await P equals C. It's quite obvious that after this await, P should be equal C. Buffer is empty. So we put something into the buffer. So let's see this buffer is filled with this data. P is not incremented yet. It's still C, right? But after increment, you can put here that it's increment. That's not necessarily. We can just put a loop invariant. Okay, so we are not finished yet because these two guys, they asked me that they live earlier. And the same with consumer. As I said that, of course, you are not doing that with a pen, piece of paper and pencil or pen. As I said, that there are special tools, semi-automated tools that allow you to do that. And then you put this thing into theorem prover, and it proves that all the states that you described, they really hold. They're held. But if it's not, then it will like alarm you saying, okay, this one is violated. And then you need to dig somehow to find out. You may do backtrace through the proof, where is the bug, okay, if any. This is so-called proof outline, it says here. So, but what one can do, like with just pen, let's say, or just looking at the source code, that's what I do sometimes, looking at your homework, is this safety property like deadlock using exclusion of configurations. Because it's easier. This can be even done just looking at. Let's prove absence of deadlock when both are waiting in that state. So the program that we have seen, producer and consumer, each of them, they include the wait statement, right? Producer is waiting when buffer is empty, and consumer is waiting when buffer is filled to consume the data. Can it happen that both are waiting and no one makes progress? Well, okay, waiting producer, when it waits, so PC should be here because it's global invariant, and P less than N, it means that we have not produced, we are still in the loop, and P not equal C, it means that buffer is full, okay? Or you can say even more precisely, P more than C, okay? if you like. And that's what I say waiting producer. So the most essential is this one, buffer is full. So similarly, we can describe waiting producer predicate saying, okay, this is like, how you call it, loop invariant for consumer, or you can put PC the same. We are still haven't consumed everything, we are still in the loop, C less than M, and saying that P is less or equal to C, or you can say more precisely P equals C. It means buffer is empty, okay? And consumer is waiting. These two guys. Now what you need to say, let's say deadlock situation when both are waiting, okay? And we put conjunction between them. This and this. And then just simply you need to Do this logic, and you will see that results is false. That implies that this situation, this state, which is described by these two predicates taken with and, never reached. And in this way, implicitly, you can prove that it never deadlocks. So again, just what is the lesson here? Lesson is that describing states in form of this programming logic, like state before, state after, and taking into account inference rules, what happens with while loop when you execute a if loop, if conditional, you can prove whether the states are really true. Okay? And either just by like simple like here, just has taken two states, waiting producer, waiting consumer, put them together, saying, is it possible to achieve these two states simultaneously at the same time? It says no, because it's false, right? Or you do this proof outline I have shown you. You mark your program states, you put them in the program and give it to special tool. And actually what this tool does, so it implies these inference rules, trying to prove to reach axioms using your predicates. It plays with your predicates, implying, and in fact, applying these inference rules is like execution. In fact, it does execution, but it's more like symbolic execution, going through like logic. Okay, if we start here, we execute this, we move there. So is it true or not? Right. Or if we want this to be true after execution if, so then it should be true before this and this. And if it happened that we describe something different there, okay, so it doesn't match. So that's what how these tools, okay, they are not considering them here, but these people who are doing with verification, they're using it. So there is example, but out of time you can take it as a, like, because there is also answer to it. And this scheduling policy about fairness and liveness property, because what we have considered so far is safety property, right? For liveness, you need notion of time. You need these causality things, you know. Also happened before, after, such things. And liveness property, very sensitive aliveness property to scheduling. To scheduler, how it schedules threads. And scheduler should be fair. It should give equal chance threads to execute, given that number of cores is small. It's like resources are limited, so scheduler defines which one should execute, and it should give them equal chance. That's fairness. And we will reason about this in the afternoon, because I'm meeting you again, right, at 3 o'clock today. Okay, see you later. You're free to go now.